Metals manufacturing accounts for about 40% of the total manufacturing output, and so it leads to at least 5% of the CO2 that's emitted in the world. That figure is very high, and we need to try and address ways of producing metals with less CO2 production.
In DARE, designing alloys for resource efficiency, what we're aiming to do is develop better materials, new materials that are more resource efficient, that result in less emissions in production, less emissions in use, and that can recycle scrap and therefore close the material life cycle.
We've put together a team that both academically and industrially represents the very best that we can.
Philosophically, we want to recycle our materials so that we take less material out of the ground, do less mining, have low arisings there, less pollution there, and also we want to reduce the amount of energy we use making primary metal and recycle the metal we already have.
We go from right at the atomic scale, where we're doing calculations about how atoms bond together, right through what we call the mesoscale, the intermediate scale, up to the full-length scale that you'll be dealing with industry, where we're really making things that industry are interested in looking at.
One of the key research themes within DARE is understanding additive manufacture, and in particular how different materials react under the quite unusual conditions they experience during this process. Once we understand that, we can start to develop new alloys specifically for this emerging technology.
That means coming up with new alloy designs, the processing route for the alloy as well, right through to be applicable in industry.
Currently, most additive manufactured parts are actually made with materials that were developed for traditional methods. So this could be things like casting, forging or rolling. In fact, these pieces here were manufactured with a titanium alloy that was developed in the 50s, sort of decades before the very first AM patents.
Titanium is mostly used in jet engines and in airframes of aircraft, where it's used on grounds of mass, the reduced mass component, less material that you have to fly, less emissions associated with flying that material around the world to take you on holiday or to your business trip or whatever it is. And our work goes from low technology readiness levels, long-range research, to quite near-term research. So on the near term, we're working with Tymet and Rolls-Royce to insert 2 new alloys into service at the moment. And here the work focuses on understanding the exact alloying effects, some little additions and how they affect the alloys, tweaking them to make them a bit better, on how the fatigue life, the life when you're cycling the load, relates to processing and how we can optimize the processing. With the new alloys potentially halving the amount of material melted to make a given component. So that's half as much material you need to melt, all the energy associated with that, to make a component, and drastically reducing the amount of machining associated with it, which saves you a lot of cost and a lot of CO2 in production as well.
Part of DARE, we're designing new alloys that are designed specifically for this additive manufacturing process. It's a really resource efficient process. It uses far less material, it makes it in one go.
In the longer term, we're working on new titanium alloys that'll dramatically increase their ability to absorb energy in an impact scenario or something like that, and achieve stronger landing gear alloys. And landing gear accounts for about 10% of the mass of a plane. So if you can reduce the mass of the landing gear, you achieve quite big benefits in terms of the overall emissions associated with flying the aircraft.
One of the reasons that this titanium alloy has been so widely used is because it undergoes an allotropic transformation. This means that the final microstructure of your finished component is much finer than the initial coarse microstructure that forms on solidification. Before we can start to develop new alloys for AM, we need to understand what are the critical material properties that determine how successful our attempts to manufacture them will be. So this could be things like the thermal expansion coefficient, the freezing range, or any allotropic transformations that take place. With better understanding of which material properties influence how easily alloys can be processed with AM, we can start to develop new alloys that are optimized for additive manufacture, or in fact optimized for the individual processes. Of course, one of the challenges is doing this without using all the rare elements, and this is an integral part of the DARE project.
The big emphasis is to develop alloys that work with the scrap stream, where you can recycle all the material you machine off when you're making something. And because titanium is very expensive, there's a huge cost and emissions benefit to being able to recycle titanium scrap. And that's very important to the competitiveness of Tymet, Doughty, the landing gear manufacturer and Rolls-Royce, and therefore for the whole UK economy and supply chain associated with aviation, which is, I mean, Rolls-Royce alone is about 2% of the UK's total exports. So it's a big deal for the UK economy.